let's move on to continental transforms and strike slip faults. Here we're looking at an excellent aerial image of the San Andreas Fault in California, and you can see the fault very clearly heading off into the distance. And there are many important continental transforms and strike slip systems. They share in common the fact that the motion along them is horizontal, but some are plate boundaries and some are not. For example, the San Andreas Fault is a transform plate boundary. The Denali Fault is not. The Queen Charlotte Fault is. The Alton-Tog Fault is not. The Red River Fault is not. The Alpine Fault is. So it may be a little bit confusing as we go back and forth between strike slip faults and transforms. The Dead Sea Fault is. The North Anatolian Fault is kind of an interesting case. It's your choice whether it's a plate boundary or not. All right, so for true transform faults, straight is actually curved because these are always going to be small circles around the Euler pole. So that means the closer that the transform is to the Euler pole, the more curved it will be, like this one. And the farther away it is, it's going to be more approximating a straight line, like that. But it's always going to be curved at the large scale. And as we said, not all strike slip faults are transform faults. So the terminology we use for strike slip faults and transform faults is we talk about right lateral faults and we talk about left lateral faults. And we talk about dextral and we talk about sinistral. Now, sinistral is an interesting word because the word sinister comes from that, because left-handed people were regarded as sinister people because they were not trained right. And we won't get into the reasons for that, but you may hear me going back and forth between right lateral, dextral, left lateral, sinistral. They're completely equivalent, right? And sometimes students will say, well, how do you know which side of the fault do you have to stand on? And the answer is it doesn't matter. The way you can tell which way the motion is standing on one side of the fault and looking at what the other side is doing, and whether, if you're standing here looking at this one, it's going to the right, and if you're standing here looking at this one, it's going to the right. So right lateral and left lateral can be uniquely defined, and you see here the focal mechanisms for both of them. Okay. So deviations in trend of the fault from a perfect circle around the Euler pole makes for localized compression, which we call transpression. That's a portmanteau for transform and compression, or extension, which is transtension, right? So here we have a strike slip with a straight fault. And of course, as I said before, they're not really straight. They have to be actually small circles around the pole of rotation. But with that detail, if there's no deviations, we will have what we could call a neutral strike slip or transform with neither compression nor extension along it. On the other hand, if we have a step on one of these faults, either to the left or the right, we can have strong compression or strong extension. And which one of these happens depends on which way the step is relative to the offset on the fault. So if you have, for example, a left step on a right lateral fault, like we have here, you will find the fault is a wider part of stuff is trying to get by another wide part, and you get kind of a compressional regime in here. So a left step on a right lateral fault or a right step on a left lateral fault is sometimes called a restraining bend. And the book talks about push-ups, And these are, mountain ranges. Imagine there are mountain ranges here. Yes, Clinton.
It's just a jump to the left.
Yeah. For those of you that know, what was that one? What was the name
Rocky
of that
Horror
movie?
Picture Show.
Rocky Horror Picture Show. Yeah. Of course, he never talked about whether it was left lateral or right lateral. But yeah, if a left step on a right lateral fault will set up a compressional regime. A right step on a right lateral fault will set up an extensional regime, which can be called a releasing bend. And sometimes we even talk about rhombochasms, right? This is a very diagrammatic, cartoonish example of what might happen between these rigid blocks. There could be a hole down to the center of the earth, which of course doesn't happen, but you get the idea. This is a very important concept because on the local scale, you may see compression and you go, oh, we must be in some sort of an orogenic system. And in fact, what you're in is a local response to a strike slip regime. Any questions? A little confusing, but if you once you get it settled in your brain, it's pretty simple. All right, so on the same system, you can have, here we've got a right lateral system, and here we've got a right step, and then we've got a left step. And on the right step, we have a releasing bend, and we have a rhombochasm or a hole, a sedimentary basin. And up here, we have a left step on a right lateral system, and we have a restraining bend and uplift and compression. We can have that. Here we see, a larger step resulting in a larger amount of compression. So the larger the step, the more is going to be the effect on the regional uplift, and likewise with extension. Okay? These are just very basic principles. All right, so the Gulf of California and the San Andreas Fault System is a good example of this, right? So here we've got the San Andreas Fault, SAF, and we're all familiar with this plate boundary. There's Cascadia. And what we've got here, this is Baja California, the Gulf of California, and we've got these are strike slip segments. This is a right lateral system. Los Angeles will be next to San Francisco in 20 million years. So if you can wait that long, you'll see that. And so what you can see is here we've got some right steps. So that is strongly extensional. And these steps are large enough that what actually goes on in there is you have short seafloor spreading segments. This is a very strongly transtensional system, which continues up into Southern California, and then it takes a left step. So there we have a mountain range. And right outside of Los Angeles is a mountain that's 10,000 feet tall. You can see the Pacific Ocean from it because of this strong compression associated with this left step on a right lateral fault. And then the San Andreas Fault goes neutral. There's relatively little compression along here, right up through San Francisco, and where it goes out to sea in Northern California. So it's a textbook example of a transform that has both right steps and left steps. Very interesting. All right, so let's look a little bit more at this transpression and transtension on the San Andreas Fault. We've already talked about this. And here we can see these short spreading segments, right? It's fairly complicated because the Colorado River, up until recently, was dumping oodles of sediment into the northern end of this basin, covering this stuff up. There's the Salton Sea. There's a very active geothermal field there. So this is strongly extensional, and GPS can measure the spreading rate of about 48 millimeters per year, Anybody want to take a guess at whether that's fast spreading, slow spreading, or intermediate spreading? Anybody got an opinion?
Well, 40 is less than the 70, so probably maybe intermediate.
Yes, this is an intermediate spreading rate. Very good. And then a little bit farther north, it sort of bends to the left, and you get this strong compression here, with what's called the transverse ranges. So there's a mountain range that goes east-west. Most of the structure in California is going sort of north-northwest, south-southeast, but here it goes locally east-west as it goes around this, what they call the Big Bend of California, which is not a river, it is a fault, part of the San Andreas Fault. All right, here it is from space. Here we can see the Gulf of California, and these are buried traces of the fault, although you can see them locally. But you can see the way they've been drawn in. These are right steps on a right lateral fault. Colorado River comes in here. This is the Colorado River Delta. It's kind of dammed up. So Salton Sea is actually below sea level. And then here you can see the Big Bend. Here you can see the transpression. Here you can see the thrust faults on the transverse ranges. Here's Los Angeles, and then way up here is San Francisco. And there's a lot of fog in the Great Valley, the Sierra Nevada. We'll talk more about that. And we've got the North American plate, and here we've got the Pacific plate. Los Angeles is the largest city on the Pacific plate, the largest plate. All right, so let's talk a little bit more about transtension, right? Right step on a right lateral fault or a left step on a left lateral fault. And it generates, this is a releasing bend, and it generates a rhombochasm. So we can see that system here. Here's the East Pacific Rise coming up in here. And down south of Baja California, the East Pacific Rise has only these small offsets. And then once you get here to the Alarcon Rise, you get these shorter and shorter spreading segments separated by longer and longer transforms. But this entire system, you're looking at right steps on a right lateral system. So Baja California was part of mainland Mexico up to about 5 million years ago. Okay. Now let's talk about flower structures. This was a concept that took me by surprise when I started teaching tectonics. And so this is complicated. Now we're actually looking at what's happening at these releasing and restraining bends. So here we're looking at a map view. This is a map view, and this is cross sections. So here we've got a right lateral system with a right step. So that's a releasing bend. That's a pull apart basin. That's a rhombochasm, some kind of an extensional basin in there. And here we've got a right lateral system with a left step. So we've got a push up or a restraining bend, right? Here they're using the word step over for bends. You know, we tend to jump around a lot. So this is another way to see it, right? Here, you know, we can show it, we can show the extension here like this or like this, right? We're not going to get too much in the details, but it's not going to be just a single fault that's showing extension. It's going to be a system of faults around either the subsiding basin or the uplifting region. Any questions about that? This is sort of building on the sort of the first order principles we've just been developing. So here we're looking at a system that's got both, you know, it's obvious. This is a left lateral system now, right? Everybody sees that? So here we've got a right step on a left lateral system. And this is obviously a compressional structure. And here we're looking at a profile across that. And here we can see the compression on a system of faults. And this is called a positive flower structure. Now, one of the things you'll notice are these symbols here. These are from engineering. It's showing flow into the page and out of the page, so that you're supposed to think of that like an arrow that you've let go from your bow, and you're seeing the feathers on the end of the arrow as it's going towards the target. And this one is the arrow's coming at you, so you're seeing the point of the arrow head coming at you. Okay, so this is a way we show motion across a strike slip or transform margin in cross section. So here we cross this contractional structure. We have a positive flower structure, all kinds of thrust faulting there. Those are thrust faults. And here with the left step on a left lateral fault, we have a negative flower structure. So we have a bunch of normal faults that merge at depth, and we can imagine what happens at even greater depth once we get below the brittle ductile transition. But these positive and negative flower structures, you'll see them a lot on geophysical profiles, reflection profiles, in different regimes. And we'll talk more about these. Any questions about these lovely flower structures? Very important point. Fun point, actually. All right, so here's another way to look at it. You know, here's obviously a left lateral system. No, I'm sorry, that's a right lateral system. So this is a left step on a right lateral system. And this is a right step on a right lateral system. And this is how we might see it. Oops, sorry. Right, there's our indicators of flow into the page and out of the page. And this is just another way to show these things. Now, to me, if I was a flower arranger, and I'm not, I would say an arrangement of flowers generally looks like a positive flower structure, right? You're always going to have the high point of the flowers in the middle, not on the sides. You could do it the other way, but it would be a little strange. So negative flower structures you'll never see in a florist. If you go to a florist, yes, Clinton.
A negative flower structure is what you send to your ex.
Yeah, I think that. Thank you for that humorous interlude. All right, so it gets even more complicated and interesting. So here we're looking at obviously a right. It looks to me like we're dealing with right lateral, left lateral, right? So if we can, yeah, there's another left lateral. There's a left lateral. These are all left lateral, but as you can see, it's incredibly complicated. All sorts of thrust faults. So you can imagine that you're doing some prospect in an oil field, and these are the sorts of things you get, these seismic reflection profiles. These are coming across. This is section 55 up here. This is section 14 down here, section 23, section 30. These are not seismic profiles, but they're similar, right? And so it changes a lot along strike. Up in the north, you've got, a pretty simple system, and then down at line 36 and 30 gets very complicated, changes very rapidly along strike. That's the point is, just having one profile across a strike slip system, especially if it's showing steps, is not going to tell you everything you need to know to understand its structure. All right, so here's a couple of examples of transpression. So one of them would be modern Southern California. This is a block diagram, something very few geologists do well. And this is Southern Oklahoma, the Fort Worth Basin, Ouachita Front, the Wichita Mountains, Arbuckles, a little bit off of due north. We'll talk about these. So here we've got the San Andreas fault system. That is right lateral, right? And it's pretty straight. And this was one of the biggest earthquakes that happened in California, magnitude 7.8 in 1857. How they got it nailed to that magnitude, I don't know, because that's before the era of modern seismology. But then here is Los Angeles, and here are a bunch of smaller structures. And here is a major thrust fault separating the San Gabriel Mountains, the big uplift, from the lowlands of Los Angeles. And you can see this is a thrust. This earthquake in 1991, which was a 5.8, was a reverse fault. And this one was 5.9 in the 1987 Whittier Narrows. That's also a thrust fault. So in detail, this is, would you say, a positive or negative flower structure? Anybody want to take a shot? Come on.
Negative.
No. This is positive.
You're
you see
talking
that
between the two right here?
this
between-
structure is, you can see the compression, right? This is thrust faults. These are thrust faults. So, you know, it looks a little bit different than the way we've been describing it, but that is a positive flower structure, if you will, on a very large scale. Right?
You're talking about the two faults to the furthest west.
Yes.
Okay.
Or actually southwest, yes. That one is a thrust fault. That one is a thrust fault. You can see the offsets. So it's a complicated diagram, but the point is to go to real examples from our basic understanding of these systems of flower structures and transpressional regimes. Does everybody see that? That if you have to, if you got a bunch of experts in a room and said, is the structure around Los Angeles a flower structure, that you would get an argument. But if I say, if this was a flower structure, would it be a negative or positive? The only possible answer, given those faults, is a positive flower structure. And that's consistent with the fact that this is part of a restraining bend. Okay? So it's complicated, but it's elegantly complicated. All right, so Los Angeles area, 16 million people live near a major restraining bend on the San Andreas Fault System, the city that waits to die. So this is the San Gabriel Mountains, right? And so here's the restraining bend. This is Los Angeles. You know, these are some of these hills that are related to the restraining bend, but this is the big mountains. And you can imagine that thrust is going right along here. This is a cartoon generated by Don Anderson. We read a paper of his about the lithosphere, or at least we talked about it. And this is the sort of a cartoonish example of the structure. So, you know, we talk about the San Andreas Fault and transforms as being plate boundaries. And of course, as we will see, it's more complicated. It always is more complicated than the way we portray it. But, you know, we want to add complications on top of a basic understanding. So here's the Salton Sea, which is kind of a rhombochasm. Okay, and so that's kind of a cartoon representation of that. All right, so that is what it looks like from downtown Los Angeles. Obviously, this is a very clear day. That's downtown Los Angeles. That is Mount San Antonio, over 10,000 feet high. Very, very strong relief in a very small area. Now here we're looking at greater detail, and we looked at this section before. In fact, this section is another way of showing what I'm showing here. So this is a geophysical profile going across here. So this is a seismic line. a lot of stations. Here is the crustal structure. We're going down to about 25 kilometers. This is the fault system. These are the earthquake focal mechanisms. You might say, oh, that looks strike slip, but remember, you're looking on the side. So in fact, you have to interpret these beach balls a little differently. This is a thrust fault when you're looking at it from in profile, as is this one. These are seismic pivot wave velocities in kilometers per second. So you'll recognize that as normal continental crustal seismic velocities. And these are the faults that the hazards community and the city of Los Angeles and the California Geologic Survey, all of these people are interested in monitoring. Okay. So this is a positive flower structure of sorts, right? So it's a complicated diagram, but you're bringing in all of the things that you understand about structure and velocity and things like that. So there it is again. And this is interpretation, right? Here, this is data, right? And with, as you can imagine, this is very focused on geophysical results, which have got to do with seismic velocities and plotting locations of earthquakes at their appropriate depths. But then we want to interpret it for the geologists. And that's what this is, right? So this is how people see it from southwest to northeast. There's the right lateral San Andreas Fault. These are the earthquakes, 7.8, 5.8, 5.9. This is the major thrust on the southern margin of the San Gabriel Mountains. Okay. Any questions about the way we go back and forth between geophysics, our fundamental understanding of these principles, and our interpretation of them?
I do have a random question.
Sure.
This one being a positive flower, with the fluid filled cracks, if it was a negative flower, would it still create voids that fill with fluids down there?
Well. So now they've obviously found something in the seismic that makes them think there's got to be some fluid down there. So here, I think this is what it is. This is a very bright reflection they got down here, and I think that's what they're interpreting, right? This is down at 15, it's almost 20 kilometers. They don't really know what that is because we've never drilled anywhere on Earth deeper than about 10 kilometers. So it's an interpretation. And so they're saying, okay, this is an active source experiment. This means that if they're getting bright reflections, they have to interpret it. So they're interpreting it as fluid-filled cracks. What fluid is it filled with? We don't know. But, this is another level of complexity that we can put on there. The geologist is rightly encouraged to ask questions about what the nature of that fluid is, but then you might even ask, are you sure it's a fluid and not something else? And you'd have to dig into that literature more to answer that question, which I have not done. All right, let's go up to southern Oklahoma. This is also considered to be a transpressional system. Only in contrast to the one in Southern California, this is an ancient one. This is something that happened in the Pennsylvanian and Permian as a result of the collision between Laurentia and Gondwana to form Pangea. So here we've got the Mississippian, which is, on the order of 350 million years ago. And here we are in the mid-Permian, about 270 million years ago. And you can see it slipped by it. All right, so let's dig into this, what we call the Southern Oklahoma Alakagen, which you all know, an Alakagen is a failed rift. This rift we haven't talked much about, but it formed at the very beginning of the Cambrian, about 540 million years ago. It's a beautiful place to go visit because you got these great big mountains in in the Wichitas, and it's a very prolific oil province. So there's been a lot of geophysics in there. So now we're zooming in. Here's the Texas-Oklahoma border. This is the panhandle of Texas. Here's the Red River. Here's the Fort Worth Basin, UTD's. That's the Munster uplift, which UTD would be right about here, because UTD is just above the Munster uplift. And you can see it's a very complicated set of faults in here. This is the Ouachita mountain thrust, main thrust, where the Ouachitas, which are very well exposed in southeastern Oklahoma and southwestern Arkansas, they're buried beneath Dallas, but they're there. And here you can see this entire system, and I think you can see it's a left lateral system. And it's a very complicated left lateral system because there's lots of structures in here that someone might interpret these as the result of sort of north-south collision. But in this model, this Hobbs et al. Model, which is fairly recent, they're interpreting it as a strike slip system overall, right? So what would you expect to be associated with this system if you took profiles? Would you expect positive or negative flower structures? Anybody want to take a shot?
Positive if it's compressional.
Yes, you're right. So once you say this is a strike slip system and there's lots of subparallel thrusts, then you're forced into the interpretation. It has to be a positive flower structures we're looking at. Now let's look at these seismic lines. We've got several here. This is 526, 133.
Can I back you up?
Yes.
I apologize. Just a simple question.
No, not at all. This is a
how am I
complicated
supposed to tell it's left lateral system?
Beg your pardon?
How do I tell it's a left lateral system?
Well, look at the arrows, right? Which way is the fault moving? If you were standing on one side of any of those faults and you were looking across at what was going on the other side, which way is the other side going?
Oh, okay. Okay, doesn't matter north or south. Okay, gotcha.
Right. If you look across any fault, if you're on the north side looking south or the south side looking north, all you're doing is paying attention to what way the material on the other side is moving.
Thank you.
Yeah, this is a key point, and it's true. Students are confused until they're all of a sudden like, I get it. So anybody else is confused, don't hesitate to ask. And there's lots of structures. Look at these anticlines and synclines. It's not just thrust faults. There's all kinds of deformation associated with this. And this is represented in the rock record. If the geology of the Pennsylvanian in particular around Dallas in southern Oklahoma and out west of Fort Worth, if you were doing work out there, you would be learning all about these sequences and this time period. Okay, it's a very short period of time as geologic time periods go. The Pennsylvanian only lasted about 25 million years. But it was short but intense. It was a really remarkable episode of Earth's tectonic history. So let's look at these profiles, and we can look back and forth at them. So here is a long line, Wichita uplift. These are the crystalline mountains. And then this is out looking into the Anadarko Basin. It's a pretty long line. Looks like it's about 50 kilometers long. Okay, and you can see the picks based on well holes. They've got a couple of wells in here. And here's what another profile that we talked about. And you look at these picks and you're going, there's not much offset there. I don't see that much offset. That looks like a little bit of a graben. Now here, this looks like a very positive. The way they're not sure about these picks, but that clearly is a reverse fault, that offset there. Right, so this is, the point is, these flower structures are more complicated than we show them to you. And as we've gone through this lecture, we just keep getting more and more complicated, right? The complexity is really quite remarkable. Right, let's move over to a different system, another famous one. This is the Dead Sea transform, which separates the African plate, and some people identify a Sinai subplate in here. This is obviously a left lateral system. You can see that from the offset between Sinai and the coast of Saudi Arabia, right? And this is left lateral, and there's a left step on a left lateral system, and that's the Gulf of Aqaba if you're Arab, or a Gulf of Eilat if you're Israeli. And it's a very deep system. And then this is the Dead Sea, the lowest place on the surface of the earth, and it is getting lower all the time because the Dead Sea just keeps evaporating. And then you go up here and take a right step on the left lateral fault. So you've got mountains up here. So basins, mountains on the same system. The Dead Sea fault is moving much slower than the San Andreas fault, at maybe a millimeter per year, whereas the San Andreas fault is moving at 20 millimeters a year. Okay, and this is the overall system. Here we're looking at it again, the Dead Sea fault system. And then it doesn't really show the left steps, but they're there. They don't have to be very big. This is Lebanon, which is a mountainous region because of that right step. And then it can be traced all the way into this plate boundary between the Arabian plate and Eurasia. And then here is the seismicity, right? Superimposed on topography. And this is, historically experienced a lot of earthquakes. So here we can see some of the damage that one of these earthquakes did 2,000 years ago. And you could say, oh, that could have been done by, invaders or whatever. But they're all knocked over in the same direction, which strongly suggests that it was an earthquake that did it. This is sort of at the boundary between archaeology and geophysics. So let's look at a little bit more geology. So here we've got the Sea of Galilee, which is a freshwater lake. The Jordan River comes in and goes out the same way. Number 2 is the Dead Sea, very famous. That's a terminal lake, very, very salty because the Jordan River ends there. So it's very salty. This is Wadi Araba here, down here. That's the strike cliff system going in there. And this is the Negev. These are transpressional structures. You can see breached anticlines in here. It's a desert, so the erosion rate is very low. All right, so this is the seismicity along the Dead Sea transform, different magnitudes. But you can see that seismicity, as we would expect, is concentrated along it. If you didn't see the geomorphology of the Dead Sea transform, you would know it was there simply from the seismicity. Now, what does the structure look like below this system? So here we're going from Israel on the Sinai microplate to Jordan, around here. So we're in the transtensional regime. And as we might expect, the crust is slightly thinned, right? It's not very thinned, but it's slightly thinned. And you look at this and you go, that's interesting. Why would the transform go there? You would think, when I started teaching this course, I was always puzzled that the the fault wouldn't be right along the crustal boundary, but it's not. And the sorts of things that we've learned in this class will help us understand why that is. Okay, let's look at another transform. So here we've got a convergent plate boundary with the Australian plate being subducted eastward beneath the Pacific plate, and up here, the Pacific plate being subducted westward beneath the Australian plate. And between the two is the Alpine Fault. New Zealand, as you know, is got North Island and South Island, and the Alpine Fault affects South Island. And you can see it spectacularly here. We're looking from south to north, all across almost all of the South Island, and this fault is simply spectacular. That's North Island, the south end of North Island there. Okay, this is the kind of structure we have down here. We're down in the south end. It's called Fjordland because there's lots of glaciers. And then we've got some nice seismic reflection profiles. Here we're not looking at depth, we're looking at two-way travel time, and you know, you can calculate what that is in meters if you wanted to. We're not going to do that here. The purpose here is to use our knowledge of flower structures to determine, are these positive or negative flower structures. There's the relative motion on the main strand of the fault, you know, going into the page and coming out, going into the page, coming out, right? This is a right lateral system, obviously, right? And let's talk about this one. Is this a negative or a positive flower structure? And it's complicated. So if you're confused,
Both.
yes, you as pointed as I think, notice the normal faults in this system, which makes you say, okay, that's a negative flower structure kind of thing. And then the overall thrust faults, which are a positive flower structure sort of thing. So you navigated that trick question very nicely. Now, another interesting aspect of transform margins is there are some kinds of continental margins that are not rifted. They result from transform motions. And in the central Atlantic, here we're looking at northeastern South America and Western Africa. You know, the way that these two continents went together, you could only cause that kind of a margin by shearing it. And here we've got these huge monster transforms and fracture zones, right? The transform margins are just between the spreading ridge. That's what these triangles are. That's showing you the spreading ridges, you know. And so this is the fracture zone, and this is the transform fault. That's the active part. And they come right to the continental margin. And this has become very important for oil exploration to understand these margins because there's a lot of oil on both sides of this system. Exxon has recently announced the discovery of a really large oil field off of Guyana, and that's associated with this system. All of these formed during the early Cretaceous opening of the South Atlantic. So here we're going to go up here to look at this region off of Ghana. And this is the Romanche fracture zone. Let's bring it back to the Romanche. So here's the Romanche fracture zone. And it can be traced basically almost onto the shore of Ghana. And then there are all of these structures associated with it. And this is how the geologists working on this see it. So here we've got the opening along a shear margin, right? A series of grabens, series of basins that link up across a right lateral transform and open and open and open. So this would be something like early Cretaceous, and this could be maybe late Cretaceous. I don't know. All right. So as I said, there's important hydrocarbon deposits here. So there's the Ivory Coast Basin, which is associated with the St. Paul fracture zone and north of the Romanche. Oops. There's the this basin here. I'm not exactly sure what it's called. The Salt Pond and Central Basins. And then there's this Benin Basin in here. So these are tremendous boons to the economies of these countries. Obviously, you know, the gift of oil can be a blessing or a curse depending on the leadership of the country, but it's there. And this structure is quite different than what we talked about with these rifted volcanic margins and these non-rifted volcanic margins. It's a very different type of continental margin and a very interesting one. Now, here we see the Gulf of Mexico, which this passive margin has been going on for 200 million years or so, but it looks different, right? This part of it looks different than this part. And we know this part is a rifted volcanic margin, and the conjugate on Yucatan must be as well, right? These somehow have to go back together. But this part is not. And you see the continental shelf, which is very broad off Texas and off Yucatan and off Florida, is not well developed off Mexico. It goes sort of straight into deep water. So you're going, that looks like a transform margin. All right, so this is the way we see it. This is from a paper that I wrote with Bill Dickinson, one of the most remarkable. He was a sedimentologically oriented tectonicist, and what we worked out from the detrital zircons was that there was this late Triassic sediment flood from an uplift in central Texas. It's called the Docan section in Texas, and then it becomes the Chinle in New Mexico and Arizona. And this is related to the very beginning activity related to the opening of the Gulf of Mexico. This is where the volcanic rifted margin was going to happen. This is where Yucatan Campeche Bank was. And for this to get out of the way, for Yucatan to move away from Texas, this had to be a transform margin, right? And this is, we're bringing it back together. Now, this idea also allowed us to think about the relationship of these basins in northern Mexico and going into Arizona, the Sabinas Basin, the Chihuahua Trough, the Bisbee Basin, the McCoy Basin, as an locogen related to this opening Gulf of Mexico system. So controversial, perhaps, but interesting. Now, this is a magnetic map of the Gulf of Mexico. It might take you a while to, you know, focus your eyes on the Rorschach test here, but you can see the outline of the state of Texas, Louisiana, Mississippi, Florida, Yucatan, Mexico. And here's that volcanic rifted margin we think is underneath Houston. And, you know, something complicated going on in here. This is deep ocean of the Gulf of Mexico, which is filled with sediments. And this is the margin that I'm talking about in Mexico. Very sharp, and as you might expect, oriented, as you might expect, a transform margin to be associated with. So when you're looking for oil offshore Mexico, you have to have kind of a different tectonic model than when you're looking for it offshore of Texas or Yucatan. All right. So let's talk very briefly about continuous versus discontinuous deformation on continents. So over and over again, we'll see that the continents behave differently to stress. The strain in the continents is more diffuse in many cases and more migratory than it is in the oceanic realm, because the oceanic realm, oceanic lithosphere, is stronger. And the ocean and continental lithosphere is weaker, which means they do different things. So here's an example of the concentration of strain along the San Andreas fault system. These are all of the earthquakes. And you can see that there's not a single line where the San Andreas fault system is. It's actually distributed into two bands. There seems to be something that's not getting disrupted in the middle, which means it must be strong. So here we've got the San Andreas fault, and we can ask the question, does the San Andreas fault mark a step in velocity between the Pacific plate and the North American plate? And if we think about just straight plate tectonic theory, it should. But does it? With GPS, we can actually answer that question. So this is the plate boundary, according to San Andreas fault. So you'd expect that the Pacific plate, PA, would be moving, that this would be like a step function, right? The Nouvelle 1A motion, the geological evidence motion would be like that, right? The Pacific plate should be like that. I'm sorry, North American plate should be relatively fixed. The Pacific plate's moving rapidly to the north. It should be a step function. These points are GPS determined measurements. So in fact, this strain is distributed across a region that's on the order of 200 kilometers wide between the Pacific plate and the North American plate, and most of it is on the North American plate. So here we see more details of this. Here we see GPS motion. It's all in the same direction, but much less motion sort of east of the fault. You can see a sort of a strain gradient across here. And I want to draw your attention in our last few minutes to talk about, these structures that are developing in Eastern California. And this is called the Walker Lane, and this is Eastern California shear zone. And they are associated with the San Andreas fault. They're taking up some of the strain. And about 25% of the relative motion between the Pacific plate and North America is now accommodated on that Walker Lane, Eastern California shear zone. We can see it here. Here we can see the velocity gradient between the San Andreas fault and the Eastern California shear zone, right? So overall, there's 40 millimeters per year motion between the Pacific and North America. And you can see that a very sharp part of the velocity gradient, the strain, is being taken up in this zone. And then in the middle, it's not moving very much. And then over in the Eastern California shear zone, it takes up another 10 millimeters per year, but again, distributed into the basin and range. This is complicated. We don't need to go into it. The PowerPoints are all on the e-learning, so you can look at that if you want. And the point is that strain is localized in the weakest region. The weakest regions tend to be thick, hot continental crust, which means thin, weak lithosphere. We're going to come back to this when we talk about orogenic systems in a week or so. The transform faults may originate at continent-ocean boundaries like the San Andreas fault, but they migrate continentward with time. And so we're going to look at a couple of examples of how the rheology of the crust affects the evolution of these transforms. So let's talk about the Southern California borderlands. This is a very interesting sort of small scale thing. So right now, this part of California is in a transpressional tectonic regime, but it wasn't always. And the Southern California borderlands are one of the best examples of that. So why do we care about the Southern California borderlands? Well, at one time, Southern California was the leading producer of oil in the world. And that was because of the Los Angeles Basin and the associated structures offshore, which became an interesting story in itself. We're not going to spend much time in there. So there's evidence that the Pacific North American motion in the Miocene time, which was on the order of 20 million years ago, was taken up farther west along what was the original plate boundary, which would have been out here. And that evidence that it was that motion occurred farther to the west is preserved in what's called the Southern California borderlands. So let's watch a short, a 4-minute video. So one of the other things that happens, I mean, we haven't, those things are sort of talking about these remarkable changes that happened after the spreading ridge started to be subducted in the trench and started converting the convergent plate margin of Western North America into a transform margin. And one of the things that happened and continuing to happen is this transform margin is moving continually into the weakest area, which right now is the Walker Lane and the Eastern California shear zone. And you can see that from the heat flow. So the heat flow map is telling you where the weakest regions are, right? The hotter rocks are, the weaker they are. So there's fairly high heat flow here, but not so high here. You know, here we are in the Western Basin Range, and there's active volcanoes there. There's hot springs. That's where the seismic activity is focused in the Basin Range, as we saw before. So this Walker Lane, Eastern California shear zone is just, started being active. And over time, we can fully expect that everything west of it will be part of the Pacific Plate, and most of the strike slip activity will be located on that. Now let's take another look at this in the Dead Sea transform. So we've asked the question, why is that transform located well to the east of the ocean-continent interface? And the same question could be asked in California with the San Andreas Fault. It's obviously got to do with the strength of the lithosphere. Oceanic lithosphere is stronger than continental lithosphere, and continental lithosphere has different strengths, right? So if we take our rheology, so here is sort of a profile from the Eastern Mediterranean into normal continental crust of the Arabian Plate. So the actual margin there is some kind of a Paleozoic passive margin. So oceanic crust and lithosphere is strong, continental crust and lithosphere is weak, and transitional crust and lithosphere is almost certainly intermediate in strength between strong oceanic lithosphere, captured here with this yield stress profile, and continental lithosphere, which has this lower crustal weakness zone. So if you're asking why is that transform fault where it is, the question is answered by looking at where is the weakest place, because that shear deformation strain is going to be concentrated along the weakest part, which from these stress profiles is here. That's where the Dead Sea transform is today because of that yield strength profile. So here, Steckler and Ten Brink have taken those stress profiles and calculated the overall strength, from the oceanic realm to the continental realm, and calculated that it looks like this is the weakest part of this region. So that's where the Dead Sea transform is going to be located. It's got nothing to do, with kind of the simple-minded considerations I had when I started being curious about this. It's got to do with these rheological considerations that we've stressed earlier in this course. So it's complicated, but interesting. I hope you appreciate. So recall what we learned about crustal rheology. We've seen this diagram before, and this is what we see at the surface. We see faults, brittle failure between rocks. But as we go deeper into the crust and encounter higher and higher temperatures, the deformation changes character. So here we've got the brittle strength zone. Here's the plastic strength. Here's a yield strength envelope for quartz and feldspar. And here's temperatures. And so, we expect that this deformation is going to change style as you go at depth from, places with faulting and cataclastites and those sorts of things. And it's going to become broader shear zones associated perhaps with partial melting. And it's going to turn listric. We talked about listric faults in discussing extensional regimes as a response to where the strength in the crust is. And there's no reason that shouldn't be associated with strike slip systems as well. I'm not going to spend time on this, but I would like to draw attention to this interesting bay. So the San Francisco Bay represents some kind of a sedimentary basin, right? And it's associated with this broad zone of the San Andreas Fault, which we can see here, right? San Francisco's there. You can actually see the fault go right through here. And there's our GPS motion. So why is San Francisco Bay there? That's clearly some kind of a transtensional regime. And is it possible that what's underneath here is a listric fault? And that's the way people are starting to see this. So this is an old idea. So we're looking across from the Pacific Ocean onto North America, and we're looking, this is the San Andreas Fault right here, and it's bringing up fragments of what's actually the Sierra Nevada batholith from farther south. You can see our little arrows, right? This is an overall right lateral system, but there's other faults besides the San Andreas associated. There's the Hayward Fault, there's the Calaveras Fault. These are well-known faults in the Bay Area. And what they've argued is that the San Francisco Bay marks the position of a basin that's associated with a listric fault, so that this vertical fault that we talk about at the surface as a transform doesn't continue as a vertical fault all the way through the lithosphere. They're showing it here sort of taking an angle, but that we could interpret that as a listric structure, and that this weakness is kind of propagating horizontally in places and then migrating in that way. It's very complicated, but very interesting. I hope you've taken away some interesting new perspective on strike slip faults and transforms and their behavior in different regions. And I think I will stop, really stop right there.